Hello, everyone. Welcome to the second part of this workshop. I hope everybody can hear me clearly. In the second part, we want to use what we've learned in the first part to just go through a workshop or a session that involves data analysis. And we're going to focus on linear regression. And this is going to be a very simple, gentle introduction to linear regression, specifically simple linear regression and multiple linear regression. Of course, we cannot teach regression in 1 hour or in less than an hour. So this is just to give you a flavor of some of the things that you can do with R, specifically using R Markdown for your classroom and for your research too. I hope that by the end of this particular session, you should be able to successfully fit a simple linear regression model and also a multiple regression model to the data. And also you should be able to use summary statistics from that particular fit to describe the relationship between a response variable, which would be your Y variable, and either one predictor variable, that is one X variable, or even in the case of multiple regression, we should be able to find the relationship between one response variable and a set of predictor variables. In today's example, we are going to use, in the case of multiple linear regression, we are going to look at an example whereby we incorporate both continuous predictor variables and also categorical predictor variables. So basically, what is simple linear regression? Simple linear regression aims to quantify or to model a relationship between one response variable and one predictor variable. If you recall from your high school algebra, we can actually model a relationship between Y and X using this particular equation. And this is the equation of a straight line function that models the relationship between Y, which is your response variable, and X, which is your predictor or independent variable. We also have other terms in this equation. You see here we have a B. This equation of Y is equals to B plus MX. And B in this case would be your intercept. So this is the value of Y when X is equals to 0. And also we have another term here, which we are calling M, which is actually the slope of the line. And this is actually what quantifies the effect of X on Y. And this is an example of how that particular linear relationship can be represented. And we are going to use this particular data set of weight and height, where weight is the response variable Y and height is the predictor variable X. And this relationship can be modeled using this particular equation of Y is equals to B plus MX. So what simple linear regression model does is just to extend this algebraic relationship between Y and X. And to do that, we are actually modeling the average response Y as a function of the predictor X using this particular equation. And just like in this equation whereby we had two parameters or two coefficients of B and M, we also do have two parameters or two coefficients of beta naught and beta 1. And for individual observations, what we say is that we have this an observation, let's say an observation xi, and this will be the value of the predictor, the predictor variable. And we can also quantify that relationship based on what the value of the response Y is using the same relationship here. So beta naught, again, this will be the baseline. So this is the value of Y when X is equals to 0. And beta 1 is actually the slope of this particular straight line function. So the goal of simple linear regression model is actually to use the available data to estimate beta naught and beta 1. These are what we call population parameters or coefficients of beta naught or beta 1. But in practice, we don't know these particular coefficients. So we have to use data to estimate beta naught and beta 1. And sometimes we'll see that those estimates will be shown by beta naught hat and beta 1 hat with a caret at the top. There's another relationship that we also have to model here, and that is the error term. And we are going to see in a moment what that error term means. Sometimes it's called the residuals. So this beta naught, as I mentioned, and beta 1, these are unknown population coefficients that we have to estimate from the data. And estimates will give us beta naught hat and beta 1 hat. And this will be estimated from the data. In simple linear regression model and also in our multiple linear regression model, we are going to use the method of least squares in order to estimate beta naught and beta 1. So I talked about residuals in this particular equation here, or the error terms. And what happens is that when we fit our data or our model to the data, in other words, when we estimate beta naught and beta 1, we can actually now come up with a relationship that is able to predict some value of the response variable yi, right? And this relationship is quite similar to the simple linear regression relationship that we've seen before. The only difference is that now we have the actual estimates of beta naught and beta 1. Right? And for each of these predictor value, we know that it has its observed response value. However, these particular estimates here also are able to give us what we call predicted values of the response. So we have the actual observed values of the response, but given this relationship, we can actually also predict what we expect to see to be the value of the response, given the estimates of beta naught and beta 1. So that means that there is actually a difference between what you have observed in the data, which is your observed value of y without the hat, and also what you're predicting based on what you've estimated in this particular coefficients. So, of course, a good estimate of beta naught and beta 1 is the one in which the observed value is as close as possible to your predicted value, which is being shown by this relationship. So that difference between what you're observing and what you're predicting based on this estimated coefficient is what we call the residual. And each predictor value will have its associated error term or its associated residual. So all these things will become a little clear when we use actually a case study. And the first case study that we're going to look at is a question that some researchers wanted to answer. And they wanted to know if there is a statistically significant relationship between height and weight. And what they did is that they took a random sample of students from a large university and measured their height, and they also measured their weight. And the data is available here in this particular public repository that you can easily access. So we're going to download that data in our R session, and we're going to attempt to answer this question. Is there a statistically significant relationship between height and weight? In other words, can we actually predict the weight of an individual based on their height? So the first thing we're going to do is actually to, and I think I forgot to mention, in order to load this particular R Markdown document that I'm using, in your files, you can select an R Markdown file that has, that is called Data Analysis Exceed. Just click on that and then it should open up in this window. You should be able to access that particular R Markdown document. Okay, so we're going to load two particular R packages that are important for one data manipulation, the tidyverse, and another one that has a data set that you can use for check on learning. And those are the two packages that we load here. This tidyverse is actually a suite of different packages, including ggplot package for making plots, table and tidyr for data manipulation, and dplyr also for data wrangling and data manipulation. So after loading those two packages of interest, we are going to load the data set, and this data set is available in this particular repository, Figshare. We're going to use this function, read CSV function, and then we're going to create this particular variable, university height weight. The next thing we're going to do is that we're going to take this university height weight. We're going to use this particular simple here to pipe that output. And the output is that we're going to remove the NS that are available, or the missing values, or the rows that have NS in the data set, just to filter it out. And then we're going to interrogate and see how the data looks like. So we're going to run that. The first output was just to read the data. We know that from this particular output here, we were able to read 20 rows and 2 columns. So we have 30 rows and 2 columns. So we do have 30 observations and 2 columns or 2 variables. And the data looks like this. This is a little bit truncated. So if we just look at head, university height weight. So we have 2 variables. We have height and weight, and that's what we're seeing here. So we have height and weight. It's head, so it's only going to show us the first 6 lines, and each row is actually an observation of height and weight. We can also examine the structure of the object, and this function is actually very helpful, especially if you have a data set that has tens of variables, and each of these variables or each of these columns has different types of data in them, either continuous floating points or characters or factors. You can actually get a general summary overview of the data by using this structure function. So if we look at this, we'll see that this is an example of a data frame of the form table, and it has 2 columns. We have the height, which is numerical, and also weight, which is numerical. We already filtered out some rows, so we only have 1 up to 28 rows in the data, because we were able to remove those rows that had NA in the data. So the next thing we're going to do is actually just to fit a linear model to this data, a simple linear regression model to the data. And we're going to use an R function called LM function. This comes with base R, so you don't need to install any specific package for that. So you'll simply put linear model LM, and then we're going to specify the variables. So we have our response variable Y as a function of our predictor variable X, and then we're going to specify the data. So that is the syntax. But before we go ahead and fit our model to the data, a simple linear regression model to the data, we have to make sure that the data that we are trying to fit the model onto meets the requirements or meets the assumptions of a simple linear regression models. And there are a couple of requirements that need to be met in order to use a simple linear regression model for your data. And we're going to check those particular requirements to see whether they are met. And if those requirements are met, then we can go ahead and interpret the coefficients that we are going to estimate when we fit our model to the data. The first thing we're going to do is actually to look at the relationship between X and Y, and we're going to check for linearity. And this is a simple linear regression model. So we want to make sure that the relationship between our predictor X and our response Y is actually linear. And we can easily check this relationship by looking at a scatter plot of X and Y. We simply plot on Y-axis weight, and then on X-axis height. In this particular plot, I'm using a function ggplot to make the plot. And what I'm simply doing is I'm supplying some argument to the function. The first thing I'm doing is supplying the data. Then I'm specifying the X variable, and then I'm specifying the Y variable also. And then I'm putting jump point to specify that I'm actually plotting some points as a scatter plot. And these are just some aesthetics to show how big I want my text to look like in this particular plot. So we're going to run that, and then we're going to examine the output. We see roughly there's a linear relationship. An increase in height in inches looks like is associated with an increase in weight for this particular sample that we've collected, but we still don't know whether this increase or this association is statistically significant or not. But at least we can see there's a linear positive relationship. There's a data point here that looks a little bit of an outlier, so this can actually skew our results a little bit, and we can go ahead and even do some outlier analysis to see whether we need to remove this point or not. For now, we see there is actually a relationship, a positive linear relationship between these 2 particular variables of interest. The next thing we are going to do is to examine the residuals, the errors that I talked about, the difference between your observed response and the predicted response that you might get based on the estimated coefficients of beta naught and beta 1. So there are 2 types of the two types of assumptions that that the errors must meet. One of them is called the independence of errors. And this simply means that there should be no relationship between your residuals and the Y variables, or the fitted values that you have. So that means that if we make a scatter plot of residuals and the fitted values, and the fitted values are the predicted values based on beta naught and beta 1, the relationship should be approximately 0. The other condition that we should look at is equal variances. So that means that if we look at these residuals for each of the values of X, the variance or the standard deviation of these particular residuals should actually be constant, or should be actually similar across different values of the predictor variables that we have. So we can actually look at these assumptions of independence of errors and equal variances by looking at a scatter plot. And this scatter plot will be the scatter plot of residuals versus the fits. And the fits are just the predicted values. The residuals, as I mentioned, those are the errors. So that means that from this particular relationship, in order to determine residuals, from this example that I showed here for residuals, right, the errors, we actually have to estimate beta naught and beta 1. And to estimate beta naught and beta 1, that means we have to fit our model to the data and estimate using the function, the method of least squares. That's why, in order to look at how residuals are, and before we actually plot the residuals versus fits, we have to actually fit the model to the data and then get beta naught and beta 1. And then from there, then we're going to, that fit is actually going to give us residuals and the fitted values. And then we can make the scatter plot. We can create the scatter plot. As I mentioned previously, we're going to use this particular function, the LM function, and then we just specify weight as a function of height, and then we specify our data, which is university height weight. So this is where we're going to fit the model. We are not yet going to interpret the summary or the fitted values or the beta naught and the beta 1s that we are getting, simply because we are still looking at the model assumptions for the simple linear regression model before we go ahead and make interpretation. So before we go ahead and answer our research question. So if we fit this and then we just print fit, we are going to see an output that shows us actually what formula we fit, which makes sense. And then we are going to get the coefficients, the estimated beta naught, the estimated y-intercept, and the estimated slope based on the data that we have. The intercept here is the beta naught, we see that, and then the height is the beta 1, the estimated beta 1. And now based on these two, what the software did was actually to calculate the residuals and also to calculate the fitted values. And those are the ones that we want to first of all visualize. Let's look at how residuals look like, and then we will go ahead and make the scatter plot of residuals versus fit. Using this function, we can easily get the predicted values or the fitted values. We can also use the residuals of fit. Another way of doing that is just putting like this and put residuals. We can easily get the residuals by subsetting using the $sign. In this case, we're just going to use these residuals, and then we're going to create a data frame of these residuals and fit. We're actually not going to create a data frame. As Chris mentioned, we can actually just create another column in the original data set that we had. So we had this data set with 2 columns. What we're simply doing is that we're creating another column of predicted values, and we are putting the output from this particular calculation, that particular predicted values. We create another column called residuals, and we're just adding that to our original data set. So our data set will have 4 columns. We have the predicted values, then we have the residuals, residual values. The next thing we want to see is just to make a scatter plot, just to show the relationship between the observed values that we have, right, and the residuals that have been created and the predicted values that have been created. We expect the predicted values to be on the straight line function. Actually, because the straight line function specifies the predicted value. It specifies the value, the new values of y, or the new values of the response. And this will come clear when you look at this particular plot. So I'm sorry, this particular piece of code here is actually quite, it has a lot of content, but I will try to really summarize what is going on here. We've already created we've added this particular columns of predicted values and the residual values. So what we're simply doing here is making a scatter plot of our data, the raw data, meaning the height, weight as a function of height on this particular university weight data, the one that we plotted before, simply before, And then in addition to this particular scatter plot that we made before, I'm actually including a straight line function. And that straight line function is just coming from the linear model fit. I'm not including any standard errors, and I'm just giving it kind of light gray color. So that is the regression line from this particular scatter plot of our raw data. And then what I'm trying to do is that I'm going just to draw lines, vertical lines that are coming from the observed, the raw data, the scatter plot data, to the straight line function using this particular function, geom segment. So just that, this one just draws a line from the data points to the straight line function. And then the next thing I'm going to do is I'm going to resize the points of the original data such that the size of this point is actually going to be, it's going to correlate to how far that particular observed response is from the predicted value, right? So if it's far away from the fit, then we're going to have a larger point, and also it's going to have a warmer color. That's what I'm simply doing that. So if we look at this, this is just to visualize the output. So originally we have these data points, but I've scaled them such that if the data point is actually quite far from what you would predict based on the expected beta naught and beta 1, we expect it to have a larger size, and also we have a longer distance, so we have larger areas. And the goal of least squares is actually just to find this regression function, or this particular regression line, straight line function, such that we minimize the total sum of this particular errors, or the total sum of these particular residuals. So we already have our residuals. Now we can go ahead and make the residuals versus fit scatter plot. Again, I'm going back to the fit. I can simply subset the residuals. I'm going back to the fit again, and I'm getting the fitted values, the predicted values, right? I'm creating a data frame of residuals and fitted values. I'm renaming the columns residuals and fitted, and then I'm just making, again, a scatter plot using geom point to show the relationship between residuals and the fitted values. If the condition of independence is met, and if the relationship, and also if the condition of independence is met, then that means that we should not see any relationship between the fitted values and the residuals that we are getting. And this is what we are seeing here. So we have the residuals on the y-axis, the fitted values on the x-axis. We don't see any relationship between the two, so that condition has been met. Another thing that we wanted to look at was the condition for the constant variance. That means that as we move across these fitted values, we should not expect to see any changes in the residuals or in the variance of the residuals. And that actually seems to be the case. However, that particular condition for constant variance sometimes is not very clear, especially if you have a smaller sample size. In this case, we only have 28. So with a larger sample size, we're able to tease out and see if there's that particular relationship between, or if the condition of non-constant variance is not met in the data. The last thing we are going to do is actually just to check the normality of errors. So we expect that the errors should have a standard normal distribution. And one of the most popular ways to do that is just to use what we call a normal probability QQ plot. So the normal probability QQ plot looks like this. It measures, it actually plots standardized residuals as a function of theoretical quantiles. The expected here is that we want to see all these particular points going on a straight line function. So we have a slight deviation. Sometimes this actually shows a bit of a skewness in our data, or some presence of outliers. And as I shown, I told you in this particular data set, we have this particular data point that seems to be an outlier, and a couple of data points. So those outliers can cause a slight deviation from this particular straight line function in this point. But by and large, most of the conditions have been met, so we can go ahead and actually answer our research question. And going back to our research question, one of the most important questions was, is height a significant linear predictor of weight? Can we predict weight given the height of an individual? The equation that we're really interested in is this particular one. It's a simple linear regression model where we are modeling weight of an individual as a function of their height. And of course, we want to estimate beta naught and beta 1. And that's what we're estimating from the data. To determine if there is a relationship between weight and height, we are actually really interested in this particular beta 1 coefficient, because this beta 1 coefficient is the effect of height on weight. So we are going to perform a hypothesis test whereby we want to determine whether this beta 1 is equals to 0 or not. So the null hypothesis is that this beta 1 is equals to 0, so there is no relationship between height and weight. What we only have is beta naught. And the alternative hypothesis is that beta 1 is not equals to 0. And of course, we estimate beta 1 now from our fit. And then we're going to compute our t-statistics. And actually what we're simply doing is that beta 1 is significantly different from 0 here. And then we're also going to get the standard error of beta 1. So under null hypothesis, this statistic T follows a T distribution. So we're only going to look into the tables, or actually the software is going to tell us the p-value associated with this. So the software will actually just calculate the probability of observing the calculated T value being equals to larger than or equals to or larger than the T, the absolute T, assuming null hypothesis, assuming that beta 1 is equals to 0. We've already fit our model to the data, and we put that fit in this particular variable fit. So we are only going to use this particular function summary to actually interrogate our fit. So when we run that, we get this output from the fit. As Chris mentioned, this actually looks like a list. It's a list-like object. It has characters. It has some numeric, something like that, looks like a table. So it actually has all the information that we need for this particular fit. The two main things that we are looking at here are the two coefficients here. We have the coefficient for the intercept, and then we have the coefficient for the height. That is beta naught and beta 1. Beta naught is the value, and each of these coefficients actually have their associated standard errors, the t-values, and the probability from a t-distribution under null hypothesis. So in this case, we see that the estimate for the y-intercept is actually statistically significant. We also look at the estimate for height. The estimate for the coefficient for height, which is beta 1, is actually statistically significant at any level of alpha, whether you take 1% or 5% alpha, you find this statistically significant. So that means that going back to our original equation, we have the value of beta naught here, we have the value of beta 1 here, and that beta 1 is significant. So there is actually a relationship between weight and height based on this particular data. And that means that this effect of height, this is actually the effect of height on weight. And we can actually go ahead and interpret this beta 1 by saying that if we increase this height, or if there's an increase of height of 1 inch, on average, the weight increases by 5.5 pounds based on this particular estimate. And that's what it's going to tell us. So the relationship is statistically significant, and this is the magnitude of that particular relationship. How strong is height actually affecting weight? 1 inch increase in height is associated with, on average, an increase of weight of 1.5 pounds. So we have already interpreted beta 1. We can look at beta naught, which is actually our y-intercept, and we can ask ourselves if beta naught is actually, if it has any meaningful interpretation. And actually it does not, because the intercept is giving us -222. And as we know, the intercept is actually the value of y when x is equals to 0. In this case, this is actually the value of height, sorry, the value of weight, which is actually negative. So that is actually not meaningful when the height is equals to 0. So for our data, that is actually not a meaningful interpretation. So we don't need to interpret beta naught. But that doesn't mean that we need to ignore beta naught, because beta naught is actually a coefficient that is very important in modeling the relationship between weight and height. So you will encounter situations, especially when you're fitting multiple regression models, whereby individually you have those coefficients that actually do not have any meaningful interpretation, but added together with other coefficients model very well the relationship that you are trying to look at between either your predictor variables and your response variables of y. The next thing we can look at is the 95% confidence interval. So we want to look at we are actually, so remember the beta one that we are actually showing is an estimate from the sample. Ideally, we want to get the beta one from the population, and we don't have resources to get the beta one from the population. So the next best thing we can do is actually just to come up with the lower limit of beta one and the upper limit of beta one, such that there is a 95% chance that the true population beta one lies within those particular and limit. And that's what we call the 95% confidence interval. In R, we can easily use this particular function, confind, to obtain the confidence intervals, the 95% confidence intervals, both for beta naught and beta one. So we can just go ahead and determine that. Of course, it's giving us the lower bound of 2.5 and 97.5 upper bound. And as expected, we see that all our estimates are within this range. So there's a 95% probability that actually the population beta naught and beta ones lie within these particular ranges that we can see here. The beauty with the regression, either simple linear regression or multiple regression, is that we can actually also make some prediction, because based on this particular relationship, we have all the unknowns that we want. We can predict the weight given a specific value of height. In this case, we're asking a question: if a student is 70 inches, what weight could we expect from this particular student? We simply just go ahead and plug in the value of height in this particular equation to obtain the weight, the predicted weight. And we can do that in R. And this is what actually Chris was talking about. We can go back to this fit, we get the coefficients, and then we actually subset using this particular first position to obtain beta naught. And then we can also go back to the fit, we get the coefficient, we subset in the second position, which is actually going to give us beta one. And we simply multiply by 70 to get the predicted weight for an individual whose height is 70 inches. So really straightforward, and this will be the prediction. It's actually good practice also to give the prediction interval, in this case 95% prediction interval, and you can easily use this particular function called predict. It turns out that this function actually takes in not just the fit, but also the prediction interval that we want, or the value that we want to predict. We have to transform that value into a data frame. So what I'm simply doing here is getting this height of 70 and then creating a data frame from that as an input, so that we can actually make a prediction based on the fit that we've already created. And I'm specifying here the interval as being predicted interval. This prediction interval will actually also give you the predicted value. So instead of going through this and creating this particular relationship, what we can do is that we can just put this prediction interval and specify our input, and then it will give us the predicted value and also the 95% prediction interval. So as expected, this is the fit that we saw from this particular equation here. So it's 161 pounds in weight. And then these are the lower bounds and the upper bounds for the 95% prediction interval. So later on, and unfortunately, in the interest of time, we're not able to go through this particular learning check. So after this, take time to attempt this learning check. And what I simply want you to do is to load this auto data set. It's contained in this particular R package. And it's a data set that contains gas mileage and horsepower and other information for about close to 400 vehicles. And I want you to perform a simple linear regression model with MPG as the response and horsepower as a predictor. So we want to see whether we can predict the MPG of a car based on the horsepower, and then attempt all these questions. Now, I'm going to go ahead and start talking about multiple linear regression model. And then when we have time, we can answer questions and also attempt the learning check. So what we've just been talking about so far is a case whereby you only have one predictor. But in practice, you usually have so many variables that you can use that are actually influencing a response variable. And that's actually what happens in practice most of the time. And a multiple linear regression model actually accounts for that, in the sense that we actually want to model one response variable as a function of a variety of predictive variables. And these particular predictive variables could be continuous variables, so they could be floating floating point numbers, or they could be categorical variables that take on different values. And we're going to see how that happens. But the method of fitting the model to the data and estimating the coefficients is actually quite similar to the simple linear regression model. The difference is actually just comes in how we are going to interpret those particular coefficients that are actually associated with the variables that we have. So a multiple linear model will take on this value. So we are modeling the mean response as a function of a couple of or several of these particular predictor variables up to predictor variable XP, and there is an error term associated with that. And each of these particular predictor variables has its own associated coefficient. And this coefficient, which we can call beta J, is actually the effect of that particular predictor variable Xj on the response variable Y, given that all the other predictors are held constant, all the other predictors are fixed. We're going to fit the model to the data, and then we're going also to, of course, the goal is to estimate this beta naught, beta 1 up to beta P. And we are still going to use the least square method to estimate those particular coefficients or the parameters of the model. So let us take a look at this using a case study. And in this particular case study too, some researchers in Sweden wanted to answer this particular question. And the question was, does smoking during pregnancy affect birth weight? So what they did is that they went about in a hospital and collected a random sample of 32 births. And they collected information based on the birth weight in grams of the baby, which is actually the response, the observed value, the observed values. And also they collected information on potential predictors. And one of them was the length of gestation in weeks, and also a potential predictor that is actually categorical, and that is the status of the mother, whether the mother was a smoker or not. So the smoking status of the mother. So this data is also available in a public repository. We are going to download it using read.csv. We expect to see 3 columns from this particular data. This is how the data looks like. And again, this is a little bit truncated because I just reduced the size of my window. But if we look at that here, we just do head. We have our births. We'll see that we have 3 variables. We have our response variable, the weight in grams, and then we have 1 predictor, gestation, and also the status. All this one, for example, is not yet in a categorical format, so we have to convert this as a categorical format. The weight and gestation are numeric, so that should be fine. So this next thing we're going to do is actually to, as I mentioned, to convert the smoke variable into a factor with 2 levels. And what I'm simply trying to do here is I'm transforming this particular, the input data set by using an if-else conditional loop. So I'm actually subsetting the smoke column only. It has values of 1 and 0. And I'm coding it such that I'm putting 1 to be the smoker, and otherwise, because I'm using if else, so the only other value would be 0. And so the 0 will be non-smoker. So that's the transformation that I'm making to the data. And then I'm seeing that this particular variable smoke has been transformed. So we have either smoker or non-smoker, and it's a factor. It's a data type of a factor over here. And then the next thing we're going to do is that we're going to put a reference level. So there's a factor of 2 levels, smoker and non-smoker. In this case, I want to put non-smoker reference to be the baseline, and then the other level to be the smoker level. So to do that, I'm using this function called relevel, and I'm putting non-smoker value as the reference value in this particular categorical variable, or in this particular factor. So one of the ways in which we are going to handle these particular categorical variables or factors is to create what we call indicator variables, or sometimes they're referred to as dummy variables. So we are going to transform that so that the software can easily understand what we are dealing with when we talk about smoker and non-smoker. So in indicator variables or in dummy variables, we are going to create this particular new variable xi such that the value of that particular variable will take on the values of 0 or 1. And we can code it such that if that particular value was originally non-smoker, then it will take on a value of 0. If that particular value is actually smoker, or the level of that particular categorical variable is actually smoker, we can actually code it as being 1. So the indicator variable will take on different values depending on the levels that we have in our categorical variable. So we are just simply transforming a little bit our factors or our categorical variable such that we have this indicator variable that takes on values of 0 and 1. So we will do that later on. And then one of the first things that I usually do when I look at this data, especially when I look at the data set that has multiple predictor variables, is to plot what I'm calling a scatter plot matrix. And we can do that using this particular function called pairs. And pairs just gives us a pairwise comparison of relationship between all the variables that I have in this particular data set. And what we have here on the y-axis is weight, on the x-axis is gestation. So I can look at them in a pairwise manner. And as expected, we see there is a linear relationship between weight and gestation. And this is expected biologically. Those particular kids who are born, or the babies who are born after full term, we expect them to have what we have like an expected weight compared to preterm babies. So there's that particular linear relationship. But we don't see a very clear relationship between weight and smoke, or gestation and the smoking status. And actually, that's the main crux of this particular research question. We want to see if there is an effect of smoking on weight after accounting for the expected effect of gestation on weight, because clearly we can see that gestation is actually positively correlated with weight. So we want to see if there's any other additional effect of smoking after accounting for the effect of gestation. So that is the central question. After taking into account the length of gestation, is there a significant difference in the average birth weight of babies born to smoking and non-smoking mothers? In other words, is smoking affecting the weight of kids? So we go ahead, we're going to fit this particular multiple linear model. We have two predictors. One is continuous, the other one is binary, or a factor with two particular levels. And then, as I mentioned, we're going to create an indicator variable for this particular factor called smoke. So we're going to have 1, the value 1 if the ith mother is actually smoking, or 0 if the ith mother doesn't smoke. So if we go back to our original regression equation, we can actually model the average birth weight as a function of we have the baseline coefficient beta naught, but also the first variable, which is the gestation beta 1 x1, plus the other variable, which is the indicator variable for the smoking status, x2 with its associated beta 2. I forgot to put here a plus, then we are supposed to have here plus the error term. So, and this is actually equivalent to this particular relationship. For mothers who smoke, we know that x2 will take on a value of 1. So instead of having x2 here, we're just going to have beta 2. And then for mothers that do not smoke, x2 is going to take on the value of 0. So we are not going to have x2 and beta 2 in this particular relationship for the mothers who smoke. So this is going to quantify, or to give us, the average birth weight of babies who are born to mothers who do not smoke. And this one will give us the average birth weight of babies whose mothers were smoking. And we can go ahead and interpret these coefficients directly. For example, if we look at beta 1, this particular beta 1 is associated with x1, which is actually now the effect of gestation on the weight of the babies. So that's what beta 1 value will tell us. And crucially, what beta 2 will tell us here is actually the difference between these two particular relationships. So if we take this value, or this particular relationship, which is actually the average birth weight of mothers who smoke minus the average birth weight of kids whose mothers do not smoke. The remainder is beta 2 coefficient. So if you want to look at the difference between the two, the difference mean birth weights for the two groups, meaning the birth weights of the kids whose mothers were smokers and the mothers who were not smokers, then we only need to focus on this particular coefficient beta 2. And that's the coefficient of interest. So we are going to determine whether this beta 2 is significantly different from 0 and or not. Again, of course, the first thing we're going to do is we're going to fit a multiple linear regression model. We're going to use this particular linear function. We're going to find the relationship of weight as a function of gestation and smoke, which is the smoking status, right? And then we're going to specify the data about smokers. So we're going to fit that, and then we're going to get just a normal linear model fit. In this case, we now have 3 coefficients instead of 2. We have the intercept, and then we have coefficients that are associated with each of the predictor variables. We have the gestation, and then we have this particular newer indicator variable that R has created called smoker. And this is actually our variable of interest or our coefficient of interest, because we already know that if we look at this particular gestation, which is, this is the value. So this is the effect of gestation on the birth weight of kids. This effect is actually statistically significant at all the levels of alpha that we can think of, right? So this levels, so that means that if we increase gestation by 1 week, that is the unit of gestation in weeks. So if gestation increases by 1 week, on average, the birth weight of these babies is going to increase by this amount, by 143 grams, right? And that is a positive coefficient. And we've seen from the scatter plot that there is a positive relationship between gestation and birth weight. And then the next thing we're going to look at is this actually the coefficient for the indicator variable for the smoking status. And it is actually negative, right? So the first thing we can make from this conclusion is that this particular coefficient is actually negative. So that means that smoking is actually associated with a decrease in the birth weight of the babies. So the babies whose mothers were smoking had a lower birth weight compared to the babies whose mothers were not smoking. And that difference is actually given by this particular value of 244 grams. And that particular difference is actually statistically significant for the different levels of alpha that we can think of. So in conclusion, we've seen that smoking is associated with a mean reduction of birth weight of about 245 grams based on this particular output. In conclusion, for the two things that we've looked at in the simple linear regression model and multiple linear regression model, we can describe the relationship between either one response and one or more either qualitative or categorical predictors using a regression model. However, we must make sure that model assumptions for a linear relationship are met before we go ahead and interpret the coefficients that we have estimated. And simply the model coefficients, the beta naught, the beta 1, the beta 2, what they're simply telling us, they're just telling us the average effect of that particular predictor on the response variable. Yep. So that's it. Any questions?